So thanks for joining. We'll get started on the fourth and last installment of the HuggingFace course this morning, night for mind. So there are two notebooks, but I'll also point to a whole bunch of additional resources from videos from the same author that I do and felt was very helpful, and point to a couple of websites that are pretty fascinating. And that will be the final section of this long journey which we started in May. So without delay, this first book we'll look at is titled DDIM inversion. We know what DDIM is. It's probabilistic modeling. It's the DDIM paper, but specifically we look at DDIM sampling, and strangely, at least it's strange for me, the DDIM inversion term means that we actually go opposite to sampling. So it's noisify in the fast AI sense, that DDIM inversion is equivalent to noisifying the image, and how the noisification process allows us to edit the images. So the setup and everything is very similar to what we've seen before, so I won't spend a lot of time. We just use the runway stable diffusion version, and then we set up the DDIM scheduler in particular from the configuration. And then this is the prompt I used at the original notebook that he had. He used beautiful R, and it's pretty neat. I used beautiful DSF with the golden R, and it gave me a different. Equivalently, it kind of seems to understand golden hour refers to either the sun coming up or the sun going down. DDIM sampling, we have looked at it many times before, and also in the DDIM paper, we realized, as has been pointed out, that it's a mixture of terminology, or actually the value which is confusingly called alpha bar in the DDPM paper is alpha. But that's something to keep in mind. But all that is hidden behind some of these library functions. So this is the plot of alpha bar or alphas in the diffusers library. We've seen this before. It starts with initial 0, no noise, to full noise at 1,000, and we saw that cosine scheduling and other stuff improves the shape of this curve, and so on and so forth. DDIM actually stands for denoising diffusion instead of probabilistic. It's implicit models, and this addition of this random noise when we denoise, that is when we go backwards from the fully noised image back to the original image. So going from XT to X0 is done this way. And each time we add a little bit of random noise, and then again denoise again. Yes. So here we have the equation for actually doing the sampling, which is through regular DDIM. And here, instead of just using the scheduler, he kind of gives us an insight into what actually happens in a combination of the noised image and the noise that the trained model predicts, and from that but keep in mind that in this case, all of this happens in the latent space. So we've already reduced it into we've already taken the large image, reduced it to its latent. Then we apply noise while training, and that's what the pre-trained model does. And the method is going backwards. So from T, we get T-1, and we repeat for each of the steps, and then we get the image back. And what we can do is we can sample, for example, with a prompt, which is watercolor painting of a beach sunset. This is a new prompt that I just provided, and here it gave me this the picture. Also wanted to try whether it can handle different styles. So palette knife painting of a waterfall, and it gives me a nice picture with these indication of the palette knife kind of techniques. Then we talk about inversion. So as I mentioned, at least it's confusing to me somewhat, because inversion, I would think, would be the term applied to sampling, because instead of noising, you are denoising. But actually inversion, DDM inversion is not sampling, but going the other direction of sampling, which would be, in a way, what Jeremy called noisifying. So what happens here is you take this original image of a dog on a piece of grass. So photograph of a puppy on the grass is what you use as the input image prompt. And we encode the image with a variational autoencode, part of the overall pipeline of diffusion. So with that, and then this scaling aspect we've seen before, and use that to sample. The fun bit is that this inversion process, and inversion, remember I keep repeating, is actually the noisify process. So here you do two things. You take the text embeddings and encode it and combine them along with the latents. And then the start latents are the latents that you provide. And then intermediate latents are the latents that you create along the way towards producing the eventual noise limit. So we are going, if you will, from x0 to xt. So 0 to t progressing noisify, and t to 0 is the sampling process. We go from 0 to t using, and because time steps typically go in the reverse direction, that is time step is, for sampling. So it goes from 1000 to 0. In this case, it goes in the other direction. So you have to reverse it. Because the pipeline scheduler time steps goes in the opposite direction, so you reverse that. And then you do the for, we'll skip the final iteration, and the code is fairly self-explanatory. Predict the noise. Predict the noise, since we're going in the noisify direction or going from x0 to xt. Then we do this classifier C guidance, and the opposite. This equation is basically a reversal or rearranging, as he says, of the update step, so to get to latents. And that's how we get this equation, that is to go from, that is to add noise to the latent. So the new latents given the old latents, right? And then we get the intermediate latents and store it in the latents, and then return the intermediate. And so you get the inverted latents. You can kind of use this function we have defined to invert and find out that the shape is the same as before. The 48 is the match dimension, and then we can view the final set of latents, which, as you can see, would just be pure noise. Now you can pass this inverted latents in the pipeline using the normal call, which means you're sampling from it and getting the image with a guidance scale of 3.5. You kind of get, oops, not exactly the we started with. Still a dog on grass, but it's very different. Right? So this is not quite the image we started with. This is because now the reason for it is DDM inversion. Inversion again is the notification, but it's true of either process, relies on the assumption that the prediction during each step is the same. And that is quite not true when we invert over only some small number of steps. Remember that we actually had 1,000 steps in the original process, but here we are only doing it over 50 or 100 time steps. And of course, we could use more time steps, as he says here, to get a more accurate thing, but we could also kind of cheat, and we could say, oh, start from step 50 and go through 50 steps. Closer to using a larger number of the steps. And we do that using the intermediate latent. So when we say start at step 50, it actually takes the latents from step 50 and then denoises that. So that's helpful because we've already gone through a substantial number of 50 steps, and then applying 50 steps is equivalent to going through the process steps, a lot many more process steps. So that's where you say start steps, and start step is 20, and then you go through 50 steps, and you get almost close to the original image. So that's the inversion process. Now, why do we go through the trouble of doing this inversion? Well, the hope is that because we have done the noisification, including a prompt, the hope is that if we now provide a new prompt, that will create the denoising process to proceed towards the new prompt and give us a new image, but with most of the rest of what we don't want to change with the new prompt remaining the same. So that's different than if we were to just do it the old-fashioned way without this inversion process. So we'll look at what's the difference. So with a new prompt, so instead of the prompt being what we had earlier, which is picture of a puppy on grass, a photograph of a puppy on grass. Here we just replace the word puppy with a cat and see what happens when we invert. And what we have here is input image prompt replace puppy with a cat, and then sample with the new prompt, and the start latents are the inverted latents, and start steps +1, and we start with step 10 in this case and go through 50 steps. And we
Srinivas, we cannot hear you anymore. No, still can't. We cannot hear you. Hey, Srinivasan, we cannot hear you. Could you hear us? Guys, can you hear me?
Yeah, I can hear you.
Okay.
Yeah, and I can't hear him either.
Yeah, he's...
Uh,
Let me try to draw something.
yeah. Oh, nice.
Can you hear me?
Yeah, we can hear you now.
Okay. So when did I lose the connection, and how far back should I go?
It has been good 2-3 minutes or more than 5
Okay.
minutes then. Yeah.
Oh, okay. So maybe I'll go back to did I get back at least to noisification here?
Yeah.
Okay, so we saw that what the inversion process or the inversion code here did is what Jeremy referred to as noisify, but keep in mind that this is in the latent space. So it just adds latents, and also it includes the classifier, the guidance part of it, because we want this process to use for prompting, right? So we do that, we run it on the latent representation of a puppy picture and get the fully noised image. Okay, so
You are not sharing your screen, Srinivasan.
Oh,
Yeah, this is a good point to start.
okay, so this, as I mentioned, is noisify in Jeremy Howard's usage, but basically is inversion, but in the latent space, right? Whereas Jeremy does it in the pixel space. Now, once you get these inverted latents, you can sample them and get the image back. But when we do that, we find that we get not the same image that we started with. Why does that happen? And he kind of explains that it happens because when we noisify, we use 1,000 steps. And when we sample here, we're just using 50 steps. So one of the ways that, excuse me, that we can improve the getting back the original image is to, since we have stored all the latents along the way, is to start part of the way through that we have already added, or start from a little less noisified image and go back to X0. So if, for example, X0 and X1000, so we could potentially start from, say, X500 and go back to X0. And now if we take 50 steps, we'll be closer to the original image than starting from X1000. So that's kind of the idea. And so here you say start step is 20 and you take 50 steps inference. That gives us back a much closer to the original image we started with. Right? Now, why do we go through all the trouble of doing this inversion? I mean, ultimately we can just noisify the latents and then provide a new prompt and get the new image, right? So why do we go through all this trouble of thinking of this inversion process? The reason for that is to keep the portions of the image that are not changed by the prompt same. So that what we want to do is, you can think of it conceptually as editing the image and keeping large portions of the image the same and just editing the portion of the image that where we change. So if we just change puppy to cat in our prompt, then you just see the cat replacing the puppy with everything else remaining the same, including, unfortunately, you can see even the chain that's not removed from the original image. And you don't cats change, but change typically, but that's kind of the issue with just changing the word puppy to cat, which is a way to not change everything else, but then you also get this artifact or from the original image. So that's the reason. And if you did it without the inversion process and just kind of providing a new prompt, then you get a cat, but there are more drastic changes in the image. The background has changed, the tree unfocus is not the same as this, whereas you can see between these two, the tree is the same. So that's kind of the advantage of the inversion way of editing the image. It leaves the portion of the image not modified by the prompt unchanged, right? So if you put all the code together and do the edit, and we say a puppy on the grass and an old gray dog on the grass, then it just replaces the gray dog. Interestingly, it changes the chain to this rope, if you will. And also, interesting to me is change the puppy on the grass. I played around with being an Alaskan Husky. I wanted to kind of change the nature of the dog, and you see the dog being an Alaskan Husky, but with no chain. And he also says, as I just mentioned, that you take more steps, you get a better performance. So you take 350 steps instead of the 50 steps that we were taking until now, and you get a much better image and much closer to the original image of the dog, right? Then a photograph of a puppy, a photograph of a white cat, but unfortunately you see this rope. And again, if you're playing with it, I didn't think of it until the image showed up, but maybe you can write a photograph of a white cat without any kind of a rope or a chain, and that might enable us to get rid of this. And this technique, he just goes on to show in the next few cells how it can be used to create the same image but with various modifications. So for example, here is a face that you load up, 512 by 512 image, and you just say face and a photograph of a face with sunglasses, and you get that. And you say a photograph of a face, a palette knife painting of a face, and you want to make it colorful, you get this. So it's kind of a neat little way, if you will, to change aspects of the image without changing many other aspects that we don't want to touch. And that's kind of the fascinating part of this DDIM inversion technique, not just DDIM sampling, but the DDIM inversion. Now, I would also point you to, this is kind of not directly related to the inversion part, but there is this whole video of progressive distillation, explanation of the progressive distillation paper by John Whitaker. In addition, he has several other videos. I would encourage you all, if you're interested, to look at these videos, because I think the whole concept of editing using diffusion, he explains very practically and with variety of methods with different pros and cons. So for example, editing images with diffusion models is an entire 20-minute video where he goes through many different techniques of editing and what are their pros and cons, and the references to the paper are also provided in the talk. There are many notebooks that this is the paper. One of them he covers is SDEdit, guided image synthesis and editing with stochastic differential equations. You kind of just draw, child drawing, and then you get converted to various different kinds of stuff, and you get the Colab implementation of the SDEdit paper. Magic Mix is another one, semantic mixing with diffusion models. And you can kind of create, you can take a watermelon and make it into a speaker or a lamp, for example. And you can take a dog and convert it into a coffee machine. So you can see that the coffee machine looks very much like a dog. And on and so forth. And then there is the whole diff edit. Again, you can just open it in Colab, and you can see instead of strawberries, you can want it with lemons. I think diff edit was something that Jeremy touched on in one of his lectures. So you can go through the video, and then I haven't yet played around with all these notebooks, but there's a tremendous number of notebooks in this edit. There's an explanation of prompt-to-prompt image editing with cross-attention control. Again, the opening in Colab and play with it. So significant resources. iMagic is something, again, that was mentioned by Jeremy very early on in the course, and there are again, notebooks associated with the iMagick implementation using stable diffusion that you can play with. And iMagick is this technique that Jeremy talked about of how you, and there are some interesting in the paper of how you just kind of change or fine tune the model and fine tune the prompt as well. And then you're able to get just from a picture of a bird, this picture of a bird spreading its wings, picture of a person, you can edit the image to make the person do a thumbs up sign, dog to a sitting dog. So all kinds of fancy editing, modification of images is possible with iMagick, and you have all the code available at hand. With it, there's another library called Unitune, I believe, and there are collab links for the notebook that you can use that as well, and the Unitune notebook. So a variety of things that you can play with, which is what is possible with all the various different videos and notebooks associated with the various papers. The goal of all of this is to allow us, using diffusion, to edit images, if you will, and get them to do what we want to change what we see from a base image. A more recent paper, or actually recent video that I saw, which also again from John Whitaker, that I would point you to also, is very interesting, because so far we have been using FID as a metric for and how to, Demi covered how to determine FID and then use FID scores to compare images. This seems to be a more recent method and technique that's called a PIC score, and this is the paper in which it appeared. And this video, kind of, as you can see, is just 2 weeks old. So you just put it out there, 15 minutes. It talks about how you can use the PIC score to distinguish between images and to score images. And this is instruct pick to pix, which is one of the techniques that for editing images. So you can see, the technique used to edit the images. The fascinating thing about this is you can edit just portions of the image. So you can just highlight a portion and say, I want this here, and it kind of just changes that. For example, you can make a rabbit appear in an image by just creating a blob here and say, show me a rabbit here and stuff, which is pretty impressive that you can do this without, having to go through Adobe Photoshop and learning all the techniques and stuff. It flops things. Of course, the control isn't fine-grained, but nevertheless, for an absolutely non-artistic person like me, it kind of is inspiring that you can play with it and get a lot of these done. The final video that I'd also point you to is the stylizing video with diffusion models that he talks about. That's also not very old. I think it was about 8 months back, how to stylize video. So again, using diffusion, but in this case, because it is video and not just editing images, it's a much more, or I shouldn't say much more, but it's a complicated. And you can see how just the show of water is changed to kind of like volcanic fire and so on and so forth. Very fascinating things you can do with diffusion and various videos and related notebooks that you can use. The last notebook that I'll kind of take you through, but the speaker of my PC isn't in good shape, so I'll try it, but I am skeptical that you folks will be able to hear it. But it's an audio-related notebook that takes us through, and it's just an example of how to use diffusion in audio. So how is audio represented? These are the things we learned, and methods to convert between raw audio and what are called spectrograms. Actually, I think Yuri was still with us. We participated way back. I think more than probably not even this year, maybe late last year. We participated in a Kaggle competition where we were trying to recognize bird sounds based on spectrograms. So at that time, I spent quite a bit of time becoming familiar with what are MEL spectrograms and how to convert sound to audio. Were you there too, Mayank, at that time? I'm not 100% sure.
No, I think I wasn't there.
Yeah, so there was like a competition on Kaggle to recognize bird sounds, and we kind of participated in it. And that's when we got exposed to the MEL spectrogram, that is how to convert audio into images and then use the images to do, because again, the techniques for classification as well as segmentation and all that is in the image space is very advanced and well developed, and you use that to actually recognize sound. So here, how to prepare a data loader with a custom collate function to convert audio slices into images, and then fine tuning on them in order based on a specific genre. And then the last part, I haven't done it because and obviously he's just doing a little bit of the stuff. There are some actual significant open libraries again that you can play with, much like we saw SVA8, iMagic, and so on and so forth with diffusion. Similarly, there is something called Refusion, which apparently does all these things with audio, but this is just a very simple notebook to get you started on that journey. So we just kind of import as usual. And there is again pre-trained audio diffusion model. So you take the diffusion pipeline and you take this pre-trained model, but obviously the model is pre-trained on instrumental hip hop, and the 256 ought to give you an indication that it's something having to do with spectrograms rather than with raw audio. So you take that and you use the pipeline as before, and you get the output. And interestingly, the output is an image. So, you can even play this. I'm going to try and play it, but I don't think it will work, in which case I will stop doing that. But let me know whether you folks can hear it. I don't think so because I'm not connected. I connect to the phone right out, but you can play with this. It's fairly simple and it doesn't take, I don't think this takes as much memory as does other notebooks, but I'm not 100% sure because some of these images, especially if you go deeper into the notebook, are pretty long or pretty. So you can kind of play the audio, and the output actually consists of two things. One is just an audio array, and the second one is a grayscale image, which is what you see here. And so this pipeline basically is, you can't use diffusion and raw audio NumPy arrays, but instead what you do is convert it to what is the spectrogram, and the spectrogram has, the conversion technique is something that you need to kind of understand. And if you're interested in the world of audio, and especially ML and AI applied to audio, then these course of lectures, which is what I went through when we were doing the Kaggle competition, to understand what a spectrogram is, to understand what's that. I'd forgotten sampling, the Nyquist theorem and so on, sampling 2x rate and the related stuff, moving from time domain to frequency domain, and all of that. This set of about 20 odd lectures is extraordinarily useful. So I'll post a link to this, but that's something, if you're interested in audio, I would highly encourage you to go through the sequence of lectures. The guy does an excellent job of starting with the basics and then taking you through all of how audio is translated and used in spectrograms, and also how AI ML is applied to audio. back to our notebook. So you see pipeline that's been pre-trained actually produces what is called a L spectrogram. And there's, you can again look at these lectures I pointed to kind of explain the entire technique of what MEL spectrograms are and how to get there, including discrete cosine transforms, which are an integral part of the whole process. But here we just say pipe.mel, and you see that it gives you all the details. It's a MEL spectrogram class. There's this hop length, as I said, Fourier transforms, and these line transforms and fast Fourier transforms are an important part. There's the sampling sampling rate, which is a key part of what we need to do in audio, then the decibels, and then the size of the image. And so you can kind of see what's the way by which, using some very simple techniques, you go from the time domain to the frequency domain. And again, that alone is not sufficient, because when we convert, we get most of the values are at extremely low values. This is 1 10 to the minus 15. And most of them are at the low end of the range. And so that is not ideal for visualization or modeling. And that's the reason we use this whole thing about MEL spectrogram. So that's the reason for the MEL spectrogram. Spectrogram is just here, but the MEL spectrogram is where we translate the audio into things which are into a spectrogram, but spectrogram focusing on the frequencies that are most that our ears are most tuned to. And here's just a picture of the various conversions that go on from raw audio to a raw spectrogram, which is actually complex, a power spectrogram, which is real valued, and then a MEL spectrogram, and then various conversions back and forth. Much of this, although I don't think the raw spectrogram is covered, but or the LFCC, but most of the rest of it is covered in the video lectures that I pointed to of how the conversions work. Luckily, we don't have to worry about all these. These are hidden behind libraries that you can use. And so you just say pipe and then MEL and then image to audio. So you can convert the image to audio or go from audio to image. And when you convert from image to audio, you just get this raw NumPy array, and then we can convert an array of audio data into spectrogram images. And not only can you do small portion, but you can also, it automatically chunks the sound and does the audio slice to image function, so that if you have a long clip of somebody talking or a bird sound, it chunks it so that you can focus on small chunks of the correct length in order to produce it. And you can do that. And once you have the image, then applying diffusion is nothing but simply following all of the diffusion techniques that we've before. So the beauty of audio processing is essentially converting audio to image, that is to a MEL spectrogram, and then all of the techniques that we have used for diffusion, all these editing techniques, everything can now be applied in the MEL spectrogram space. And again, I can't play this, but you can kind of what it points out by this is the sampling rate. If you're dealing with sound, becomes very important. So if you do a 2x speed, then obviously the sounds become high pitched and so on. And you can fine tune the pipeline. There's a whole data set that he points to where you can have 15 genres. This particular portion of the notebook, I think, takes a long time. I don't know how much it does take significantly too, because each of these is about half a gig. And you can see that there are lots of different genres, and you can fine tune. He has actually already fine tuned on, I believe, the electronic. I also fine tuned on classical and got interesting results. Interesting in the sense that I'm not music expert, but I was able to generate something which remotely sounded classical. So you can, data set has the raw audio arrays and how to make sure that the sampling is the same as what it was originally. And then you can kind of convert it to the spectrogram, get the audio array, load it with TWIML, and then view the first slice. And then obviously we need, as I mentioned, to make sure that the sampling rate is the same as original. So we kind of determine the original sampling rate and view the first slice. And then we can use torch audio. So there is also something called, just like torch vision, there's torch audio to deal with the audio transforms. And you can resample the pipes MEL spectrogram to turn the audio into an image. You can also kind of create, and the next part is the important part, which is to say, how do you collate the MEL spectrogram? Because remember that, and we spent quite a bit of time understanding how the collate function works in PyTorch. So in this case, we'll need to collate the spectrogram images, first convert them to tensors, then rescale them, and then stack them into a batch. So this is something we've seen in quite some detail in the Jeremy Howard course. And you can see 2T is the part converts it to a tensor after applying to a tensor, and then convert it to -1 to 1. So image, convert the audio array into an image, and then scale it for each of them, and then return the stat as audio images. Then you create a batch size. With Andhra that's chosen, he chooses electronic, and you can try different things. I tried classical. And then you use the whole training loop to kind of train using our diffusion techniques. But obviously, as if, it would have taken me a very long time to train this, because each epoch was significant. So he says, don't do that. I've already pre-trained the pipeline. You can just use that, load that, and then, play the output. And again, you can see it goes through the 1,000 steps. You need to provide the rate. And then you can also make, once you've created this sample, you can make a larger sample. Here, just a heads up that his original code uses sample size, but for some reason that doesn't seem to work because these are integers. But knowing that the sample size is just that its outputs is 256 by 256, so all you're trying to do here is keep the y-axis between 256 and then stretch out the x by making it about 4 times longer. So all it does is just stacks the same image 4 times long the x dimension. And that way you can play a longer sequence and just what a 256 spectrogram image will be. That's it. And then, obviously you can say I tried it with classical and was able to produce images. I used a V100, so this part again, if on your it won't work. Requires a minimum V100 to train. Otherwise, it takes. I tried with a T4, and that took me, or it indicated it would take me 1.5 hours to train, and then get the output. And so that's all, of course, pushing to hub if possible as well. So that's kind of what you can begin to do with audio. And again, as with many things, there's a whole audio diffusion pipeline available. There is this is audio pointer, and this diffusion is again a very interesting library, open source. So you can go look at the code for diffusion, and this AI will literally sing whatever you type. So again, something additional that you can play with that I guess people have created various things with as well. And the code for it is available if you wish to play with it. The one final thing I wanted to point to, and by the way, this is the video with coherence guidance. So this is the last thing I pointed to with respect to the not just image but stylizing video. So this is the code for stylizing the video. The one final thing I wanted to point to, which I thought was just incredible, is a guy has a slide where he tracks the papers on diffusion models. And what's fascinating to me about this is that this site pretty much automatically loads all of the recent papers on diffusion. I haven't seen something like this. Maybe there's a site like this for LLM papers too that I'd like my hands on, but that I thought was very fascinating. So this guy's blog, but it just every day, whatever an archive, whatever diffusion model related papers are posted, I guess he just grabs them and puts them on this site, pointed to it, which I thought was very fascinating. So you can just kind of browse through this on a month-by-month basis and see what are all the papers being published in archive. So one location, instead of searching and you don't even know what, you can just skim this, and I was just blown away. It was like every single day of the week that papers get added on diffusion. All of them show up here. And also, I don't believe I might. There's one additional thing I found in all my getting more familiar. That is, can you still see my screen?
Yeah.
Okay, so this particular paper, understanding diffusion models, a unified perspective. I haven't gone through it, but I found it in as part of I forget which video lecture that I was going through and stuff. But this write-up is very useful, at least to me, because it goes through the math extremely step by step. And I know Mayank had pointed to, and I had listened to, and I would encourage people to also look at CVPR. There are a couple of tutorials in 2023. There is one in 2022. There is one, and I would encourage you to listen to both of them, but because they are kind of complementary. 2023 is much more application oriented. 2022 covers the basics, but the basics are heavily math oriented. And what I think is useful in this particular paper, I'll post a link to it, is the fact that here he takes you through the math step by step instead of in the tutorial where it's just like, more of the explanation behind the math, not so much details of the math. But here the details of the math are covered in a very step-by-step manner. And what's fascinating is that it covers the entire thing, going from generative models, elbow, evidence lower bound, VAE, hierarchical VAE, variational diffusion models, whole-based generative models, guidance, classified guidance, classified guidance. So it just completely covers all of the math of the diffusion concepts. So and I plan to do this, haven't done it yet, is really go through this to get a good math grasp of what's going on. And I think I really appreciate this particular paper in how much detail he's gone through it. So if you're interested, I can post the link to this paper as well. I don't know that I'll remember all of it, but at least get it into my head. Then I can recall it.
Yeah, that'd be great. Thanks.
Just about a year back. So that's it. Thanks for joining me on this kind of long May to November journey, but I think that's pretty much the end of the lectures that I was planning to go through. We kind of stretched it to 4 more using HuggingFace diffusion, but I think that there are many things pointed to in the usage Hugging Face pipelines that I thought was pretty useful, besides just getting into the details of how stable diffusion is implemented, which is what we went through on the Jeremy Howard's course. Any questions, comments, final thoughts?
Yeah, thank you. This series has been really interesting. I've learned a lot. It's been great to see the details of a lot of this stuff.
Yep, kind of, behind the scenes, and also kind of exposes you to a lot of different details. I mean, don't know that anybody would necessarily have to code stable diffusion from scratch, but knowing all the different pieces and how they all come together. Unfortunately, Demi didn't kind of quite get into the prompt, and because it was textual and he kind of deferred the NLP piece. But that's where I think a little bit of the videos that we looked at from John Whitaker helped. I think John Whitaker is also writing a book about the whole diffusion and generative AI. So that's something to keep an eye out for. And John covers in some of the videos that I pointed to, and all of the videos are actually links from his other videos and from the notebook. So nothing that I pointed to other than this one link of all the different papers and this Google paper. The rest of it you ought to be able to get to from John's videos. So you should be also able to get hold of a lot of the most recent research that you were interested in from the site that just updates on a daily basis almost.
So this is definitely great. There are a lot of people now using diffusion in known picture generation, like weather models, stuff like that. And that's my plan to use it there, but I haven't done it yet.
Mayank, you were saying?
Yeah, I was commenting on how helpful it has been for the stuff that we do, and for understanding deeply the diffusion pipelines inside the Hugging Face diffusion library, and the Jeremy Howard's course that we did earlier. So it has been a helpful journey, a helpful ride.
Yep. Thanks for staying with it all the way. Prior experience says, we may start with 10 or 15, but eventually it's like whittles down. But thanks for staying with me through that. And, at least for me, trying to understand and then explain makes me, forces me into the kind of really grasping things better, or kind of pondering the question. For example, I still haven't found the answer to what Emily asked, I think, a couple of lectures back. Although I think I went back, or the question she asked was, why there's a difference in predicting using noise prediction versus predicting image. But a related kind of question, I went back and listened to the couple of lectures that Jeremy had where he talks about, I forget it was referred to as the Karas paper. And if you recall, one of the things because I went back to it, I can remember it now. He talks about how, how the Karas guys, or in that paper, how they use a modification of learning different things at different phases of the diffusion process. For example, in the early phase, by early phase, I mean when the pure image is or low values of T, if you will, so closer to the clean image, it's much harder to predict the noise because the noise is very small, right? So it's harder to predict the noise. So there in the Karef paper, they use a model to predict the noise. But in the later portions of the diffusion process, when it's all noise, it becomes easy for the model to predict the noise. So they predict the actual image, the noisified image. So while it's not an answer to any question, it actually prompts interesting saying, oh, predicting different things, different phases is actually better as characteristic just because of the simple thing that you want the model to predict whatever is harder towards the end. So that is kind of a hint towards, beginning to understand the reason of why predicting noise in some cases or predicting the noised image is good or better. So things like that, emerge more in discussion rather than in just, for me, sitting and just individually going through stuff. So in that sense, I think, having folks join in and ask questions and or discuss is, as we have seen in the casual competition as well, a much better way, at least for me to learn. So thanks for staying with it, all these. Okay, with that, we are done. And again, thanks to everybody, and see you all in the casual meeting.
Yep. Thanks.
Yeah, thank you.